Greetings to one and all. I welcome you all to our webinar titled Sensors to Deep Learning, Product-Centric Approach to Tomorrow's Innovation. My name is Arvind, and I'll be your host today. We are privileged to have with us two distinguished speakers, Dr. Raj Gupta and Sohag Desai. Raj Gupta, VP GM of Smart City, Smart Health, and Industry 4.0 Business Unit at Multicoreware. He's also a renowned expert in the field of deep learning. Sohag Desai, who heads advanced engineering projects, is an industry veteran of many product launches. Now, let us start with a brief introduction to the industry and why we need this topic today. In the modern era, sensors play a pivotal role in gathering data from the physical world. This data is the lifeblood of modern industries driving everything. On the other hand, we have deep learning, a subset of machine learning that uses neural networks to model and recognize complex patterns and draw inferences. Deep learning has been making waves in various sectors, from healthcare to finance, and now it's set to revolutionize the way we use sensor data. But why do we need a product-centric approach? Well, as the name suggests, this approach puts the product at the heart of everything. It's about understanding what the product needs to do, what value it needs to provide, and then using the appropriate technology to make that happen. In essence, it's all about creating products that are not just smart, but also intuitive and user-friendly. Products that don't collect data, but use it in ways that understand what the user needs and creates value. And that is why we are here today, to explore how sensors and deep learning can come together in a product-centric way to drive the innovation of tomorrow. Now, without further ado, let's dive into the webinar with Dr. Raj Gupta and Sohag Desai. If you have any questions, you can use the chat box to convey them, and we will be answering them towards the end of the webinar. Over to you, Raj and Sohag.
Good morning, everyone. I'm Dr. Raj Gupta, VP GM of Multicoreware SSI Business Unit. I'm delighted to be here with my colleague Sohag Desai, Head of Advanced Engineering Projects in SSIB.
Thank you, Raj. It's a pleasure to be here. Today, we're going to take you on a journey from sensors to deep learning as it applies to key use cases in three vertical areas: Smart City, Smart Health, and Industry 4.0. We'll talk more about the use cases later in the webinar, but for now, let me introduce them. In Smart City, we will analyze the video surveillance use case and address the question, how can video surveillance detect objects more accurately? In Smart Health, we'll tackle the vital signs detection use case and address the question, can we detect vital signs without having any wearable technology for the humans? In Industry 4.0, we'll try and figure out what challenges we encounter when trying to detect anomalies without human intervention in heavy machinery.
That's right, Sohag. We will start with the basics, collecting data. Regarding of the use case, data need to be collected, and this can be achieved by using sensors such as RGB, LiDAR, radar, time of flight, and IoT sensors. Data has been called the new oil because of its role, fueling insights. However, data is not useful in its raw state. It needs to be refined, processed, and turned into something useful. Its value lies in its potential. Data forms the foundation of any system that attempts to model the real world. What happens after we collect the data, Sohag?
Raj, from there, we'll move on to making sense of the data. Data can take different forms. For example, 2D images, 3D point clouds, unstructured text, database records, raw signals and waveforms emitted by IoT sensors. Each of these types of data requires specific technologies to manipulate and transform them into a form that can be consumed by deep learning models upstream. We'll discuss how we can leverage technologies to process this data, develop inference models, and chain them together in a pipeline to create powerful solutions. Raj, please tell us why it is important to think in a product-centric manner.
Right, Sohag. It is one thing to develop the model for R&D purpose, It is quite another matter to create a commercially viable product. A product need to operate in the cost-effective form, leveraging the available hardware resources. This could involve parallelizing the application software and leverage into modules that are best run separately on CPU, GPU, DSP processors, and utilizing multiple cores. A product's performance characteristics need to be energy efficient as possible, highly responsive to be accepted in the market. In order to achieve this, optimization such as quantization and pruning should be used. These techniques has been proven to improve algorithm throughput by 2x, 5x, or even 10x or more, boost accuracy and performance without increasing the hardware cost. What did I miss out, Sohag?
Raj, let's not forget about the presentation of the solution to the end customer. Unless a product is usable and intuitive, it will remain shelfware, or worse, result in poor customer satisfaction and create a negative impression of your company. It is critical to spend an adequate number of cycles to ensure that the user experience is well thought out and optimal, and that the user interface is intuitive and responsive. Raj, I know you are an expert in computer vision, AR, and VR. Would you like to add some thoughts on the presentation aspect?
Absolutely. Modern user interface involves 3D rendering in virtual environment and using a digital twin, which is technically a exact virtual replica of an object, process, or the system that has twinned to its counterpart in the real world through data and information feeds. These technologies are revolutionizing the way we interact with our machines, the way we visualize the problem, and the solution in all the three verticals. I'll let you talk about final steps, Sohag.
Sure, Raj. As the last step in the journey from sensors to deep learning, we'll discuss how all these technologies can be brought to market in the form of a product. Our product centric approach has successfully assisted various companies in their quest. Why don't you summarize it for us, Raj?
Sure, whether you are looking to reduce your time to market by up to 10, 20, or 50% or more, I just want to learn more about the latest advancements in deep learning or machine learning as applied to domains smart cities, smart health, and Industry 4.0. This seminar is for you. As we dive deeper into our discussions, let's take a moment to look at some key use cases in smart cities, smart health, and Industry 4.0. I want to emphasize that the approach we'll be taking here is applicable to all the products and use cases in the respective domains involving the journey from sensors to deep learning. However, for the today's, we have taken three use cases to illustrate the technical challenges one will face. In smart cities, we examine a video surveillance use case, which is crucial importance for home and office security system. The important question here is how can we detect objects more accurately? In smart health, we dig into vital sign detection, extremely important to elderly care facilities and senior centers. The question to be answered here is can we detect vital signs without requiring subjects to use wearables? In Industry 4.0, we will investigate how can enhance worker safety by enabling the detection of anomalies in heavy machinery without human intervention with the use of digital twin. Do you agree, Soha?
Absolutely, Raj. Looking at use cases is a powerful way to give us insights and help us make more informed technology decisions.
As we move into the next segments of our discussion, let's delve into technical aspects of these use cases. Soha, could you share your insights on the underlying technologies area that come into play to support these and similar use cases?
Absolutely, Raj. Each of these use cases require contributions from multiple technologies. We've organized them into the following: data engineering, sensors and sensor fusion engineering, embedded software, compilers and platforms, applications and algorithms, and frameworks and tools. In that order, they run the entire gamut of the software stack, starting from the hardware and moving into the cloud. Not to forget the non-negotiable need to comply with regulatory standards, security, and privacy requirements. We must ensure that our solutions adhere to all relevant laws and regulations, such as HIPAA, GDPR, Sarbanes-Oxley, PCI, and many others.
That's a great point, Sohag. At Multicoreware, we have been able to overcome these challenges through our technical expertise. Could you share examples of how we have applied this expertise?
Sure, Raj. Let's start with the foundation of it all, data. When it comes to data, there are certain common considerations that come into play when tackling any use case in this area. Number one, how do we store the data and scale the storage and handling? How do we ensure that data is clean, normalized, and not incomplete? Our models need annotated data to train them. How do we label the data? Since it's impractical to capture every real-world situation in a data set, how do we augment our data sets to generate synthetic data, simulating conditions that may not have been captured in our original data sets? What about data confidentiality and compliance to regulatory standards such as HIPAA? As an aside, in the case of smart health applications, personally identifiable information, PII, and personal health information, PHI, must be stored separately with access controls, accounting, and audit trails to the data repositories. Finally, we must take care of data handling infrastructure. Raj, perhaps you can give us insight into the specific considerations in each of the use cases that we are discussing.
Sure, Sohag. In the video surveillance object detection use case, key data-related considerations include ensuring that the boundary box around each human figure fit tightly to prevent false identifications. The system must be able to handle patterns that were not observed during the training process or tail cases. An important challenge is maintaining data heterogeneity to prevent performance degradation of the model.
Interesting, Raj. What about in the vital sign detection case for detecting heart rate and respiratory rate without a wearable? What are some of the problems that need to be overcome?
In the vital sign detection use case, important considerations are: can the vitals be detected when the object is moving? Can we ensure the privacy of the subject?
I'll bet there are very different issues that are encountered in the digital twin anomaly detection use case.
Indeed, here important considerations include the location of the sensor, modeling the physical properties of the object to predict the behavior in the real world environment.
Thanks for the elaboration, Raj. Next, let's talk about how we can collect this data. And to do that, we use sensors. Sensors are at the heart of data acquisition. Furthermore, one or more sensors could be involved, such as RGB cameras and radars. Considerations broadly at this level include ensuring that there is synchronicity between the disparate data feeds to ensure data integrity. Hence, sensor fusion comes into play. Further, these sensors are active devices and could consume significant power. It is important to ensure that power consumption remains bounded. Finally, it is essential to establish feedback mechanisms to enable accuracy and completeness of data collection. How about the specific use case level considerations, Raj?
Certainly, Swahab, each use case has its own technical challenges for this technological layer. In the video surveillance use case, there could be multiple camera feeds involved or camera and LiDAR feeds involved. Each camera would provide a different angle. It is important that these feeds are synchronized and that when combined, they make a coherent 3D image. If the images are taken in low lighting conditions, they could be grainy and dim, resulting in a lot of noise. Therefore, noise removal is an important aspect to be considered.
That's interesting, Raj. How about the vital signs detection use case? What kind of problems and challenges are involved there?
For the vital signs detection case, to implement it without a variable and still be able to detect heart rate and respiratory at a 2 to 3 meter distance, the solutions call for a low power UWB or FMCW radar. To ensure range accuracies, classification of detection, it is crucial to calibrate the radar sensor. If multiple people are in the field of view of the radar, to distinguish them, it may be necessary to use our cascaded radar concepts.
I see that there are very different priorities and issues to be solved for sensors across all the use cases. What about for the anomaly detection case?
I won't sugarcoat it. There are a lot of challenges, but I'll just touch upon three of them. The basic initial consideration is to be able to detect the object. It is therefore incumbent upon the system to strategically position the sensors to provide comprehensive coverage of the physical space or machinery. Factors like sensor range, resolution, and environment geometry comes into play when deciding where to place sensors. Next, ensuring that the digital twin accuracy represent the physical environment is of crucial importance. The digital twin should familiarize miner the real world system for effective anomaly detection. Not only should it mirror the object statically, but the model should change in real time in respect to the state that the object is being subjected to it in the real world. Finally, before one knows if the behavior is anomalous, one need to know what the normal behavior is. Therefore, historically, data need to be gathered for model training. This data should include normal operating conditions as well as example of anomalies. Anomalies may be rare events, defects, or deviation from expected behavior.
Wow, Raj, what a lot of aspects need to be taken care of to deliver a product. And this is the domain of embedded systems engineering. And this is where we bridge the gap between hardware and software. At this layer, edge computing plays a significant role. Some questions we need to answer for this layer are: what functionality should we place at the edge versus in the server or in the cloud? How can we optimize our resources given the fact that any functionality at the edge will be on a device with very limited resources? What power constraints are we dealing with? Software at this layer will need to enable data acquisition by driving the sensors as well as pushing control signals to the device via actuators. So power handling becomes crucial. The overall system must be able to handle real-time data flows. Therefore, we must use RTOSs or real-time operating systems. Finally, an important consideration is the cost of data transmission, not only from the dollars and cents perspective, but also from a performance perspective. The system must be designed to reduce latency, so the architecture must factor in adequate buffering and the ability to deliver data just in time via content delivery networks to the cloud. What are the gotchas we need to look out for in each use case, Raj?
Those are really eye-opening issues, Sohag. As you mentioned, each use case has additional challenge to handle. For video surveillance use case, the video need to have a resolution of 4K to achieve the most accurate results. On the other hand, the environment has severe resource constraints. The design should address these conditions. Remember, when we talk about sensor layer, we mentioned the need to synchronize the feed in case of multiple sensors. Well, to support that requirement, the embedded layer must implement the data synchronization. For vital sign monitoring use case, power management is important consideration as this use case is about sensors that are located inside a building, such as assisted care facility. A key outcome of this use case is to raise an alarm which an evaluated or anomaly low heart rate or respiratory rate is detected. The embedded software must therefore have the capability to set thresholds and raise alarms when the threshold is breached. For the anomaly detection use case, power optimization is an important consideration as the power budget in an industrial facility is limited. Additionally, to feed the digital twin with real-time data from multiple sensors, it is necessary to multiplex the data streams. So all the data fetched from the sensors need to be time sliced. Finally, the data has to be streamed to the server or the cloud. So, messaging protocols such as MQTT has to be employed.
Let us move up the software stack now, Raj, and talk about platform and compiler level considerations. Important aspects at this layer involve being able to refactor and compile the software to take full advantage of the available hardware, such as CPUs, GPUs, DSPs, and FPGAs, and have it run on multiple cores to achieve parallelization and concurrent execution. Each of these hardware types execute certain types of functionality optimally. For example, CPUs are great for general purpose compute tasks, GPUs for vector, matrix, and image operations, and DSPs for high speed processing of numeric data representing analog signals in real time. Compilers can automate some of this, but oftentimes it's up to the application developer. As a side note, that is in fact one of Multicoreware's core competencies, which is captured in its very name. Coming back to the platform, it must be capable of scaling up and down to optimally utilize the available hardware. When the demand is high, the platform must rapidly enable additional resources to come online. When the demand reduces, the platform should be able to deactivate resources to avoid using them unnecessarily and thus save costs. Often applications are required to run on disparate platforms. Hence, a key consideration is porting and cross-compilation. By the way, this applies to third-party libraries that are used within the application as well. If binaries for these libraries don't exist for any platform, they must be recompiled for that platform from the source code. Additionally, these libraries must be optimized in the same way as the application to take full advantage of the available hardware. If we successfully handle all of the items mentioned, the platform and compiler layer will enable that application to have the lowest latency possible to improve the user experience. Now, I'm sure there are additional use case specific challenges that you will be able to point out at this layer, Raj. Can you elaborate?
Sure, Sohab. For the video surveillance use case, it's important to become optimize the ONX platform. ONX is an open format for open neural network exchange built to represent machine learning models. Representing a deep learning model in ONX format make it easier to access hardware optimizations. Further, the software should be optimized for DSP and FPGA. You describe the advantage of CPU, GPUs, and DSP. Let me say a few words on FPGA. FPGA is a different beast. When the code is executed on the FPGA, it is not executed in the same sense that compact and assembled instructions execute on the CPU and GPU. Instead, the data flows through customized pipeline on the FPGA that match the operations expressed in the software. Because the data flow pipeline hardware matches the software control, overhead is eliminated, which results in improved performance and efficiency. For the vital sign monitor use case, important considerations are the platform should allow deployment of processes close to the sensors to the process the data. The platform must enable power management as the sensor deploy in the facilities are battery operated. The life of battery has to be maximized. Also, the performance of the system must be accelerated. In the anomaly detection use case, it is necessary to leverage the cross compilation as often there are sensors from multiple vendors involvement. This may require porting the application to another architecture. Also, sending a notification upstream as soon as the anomaly is identified is of parametric importance for this use case. The system cannot tolerate high latencies. In a nutshell, there are some of the platforms and combined level consideration as they apply to each use case. What next, Sohag?
Okay, Raj, let's move up the software stack and talk about applications and algorithms. This is the layer in which the customer has the most direct touch points. Some of the important design decisions that need to be made at this layer include identifying the specific deep learning models to use. Sometimes a combination of models may need to be used, as a single model cannot suffice. We need to come up with approaches that leverage the strength of each model to apply to the problem it best addresses. For example, for handling 2D image data related to intelligent video surveillance, a variety of DL models are used, including convolutional neural networks or CNNs, specifically the ResNet 18, 34, and 50 models, recurrent neural networks, RNNs, long short-term memory or LSTMs, gated recurrent units, GRUs, simple recurrent units, SRUs, and generative adversarial networks such as GANs. Another decision to be made is identifying which applications to integrate, since the application being built may need to interoperate with other applications in the ecosystem. How to optimize and tune the performance of the system is always of paramount importance. Techniques such as quantization and pruning can be employed. Quantization is a technique to reduce the computational and memory costs of running inferences by representing the weights and activations with low precision data types like 8-bit integer or int8 instead of the usual 32-bit floating point or float32. This greatly improves the performance since most processing units are optimized for integer processing. Pruning, on the other hand, is a process of removing weight connections in a network to increase inference speed and decrease model storage size. In general, neural networks are very over-parameterized. Pruning a network can be thought of as removing unused parameters from the over-parameterized network. In addition, how to feed back information into the models to continuously improve them, in effect, using the data that is coming in production and retraining the model based on new activity. This involves setting up a mechanism to feed back data into the training pipeline. Finally, it is extremely important to make sure that the data that is being used to train the models is not skewed in any dimension to prevent bias. What are the design considerations for each use case, Raj?
Good point, Sohag. For the video surveillance use case, one aspect derives directly from the continuous learning point you made, handling tail cases. In general, it is difficult to provide training data for these cases, so we have to rely on continuous learning to let the system eventually be able to handle the outliers. Another requirement that falls out of what you mentioned is creating demographic models to ensure unintentional biases do not make their ways into the training data, causing the model to perform poorly when deployed in the real world. For vital sign detection, the ability to detect HR and RR directly from the raw data may be sufficient. No DL environment is here. For anomaly detection, the important consideration is the ability to correctly replicate the physical entity in the virtual world. If anomaly detection is to be done for a part on the assembly line, the ability to dimension the moving part through the assembly line is critical. Over to you, Swag back.
All right, Raj. Now we come to the final step in the journey, the frameworks and tools that are necessary to implement the system. These frameworks must support distributed computing environments in order to scale when the volume of data becomes large. The framework must also support the ability to run pre-trained models and serve them up at runtime. They must integrate with diverse data types, like we mentioned earlier. They must provide a platform for security and compliance. They must manage all resources system-wide, and they must support the user interface infrastructure. I wonder how these requirements manifest per use case, Raj.
The requirements at the use case level largely mirror what you described, Sohag. For video surveillance use case, there need to be distributed system for video management solutions. Video clips and recording must be stored in the cloud. For vital sign detection use case, privacy and security of the data is of utmost importance. As this is sensitive health information, the data must typically be encrypted and stored, and the framework must support encryption. For the anomaly detection use case, the data coming from diverse sources must be considered. The framework must also enable two-way transfer of data to ensure that digital twin is uploaded in the real time. And if configuration changes are made to digital twin to remedify any detected anomaly, these changes are conveyed into the physical entity.
Thank you, Raj, for that explanation. Well, that was quite a journey we undertook, all the way from data to sensors to embedded systems to applications and algorithms, and finally to frameworks and tools. There is so much more to say about each of these, but I guess that's as much time as we have right now to cover the technology areas involved in our journey from sensors to deep learning. Now, let's talk about how to develop a product to support these use cases. To discuss that, let me request our host Arvind to set the stage.
Thank you, Sohag. Now, let's dive into our product development approach. Can you describe what a typical product development cycle looks like?
Sure. Here's a flowchart depicting a generic product development cycle. As you can see, the product development cycle starts with the customer. The product manager collects product requirements and engages with the solutions architect to determine the technical requirements. The project manager identifies the technical resources and plans the development schedule. Further, the project manager must have the capability of deploying one or more engineering groups that are relevant to the technology that is being developed for the product, and activating or deactivating them and scaling them up or down as necessary based on the product demands.
Thanks, Sohag. However, to me, this seems to be fairly abstract. From your previous experience, could you describe a product development cycle which makes it more real for the audience?
Sure, Arvind. Let us take as an example vital signs detection with an ultra-wideband radar use case.
That sounds good, Sohag. Could you tell me what steps are involved?
The first step is requirements gathering. For this use case in particular, first, the capabilities of the radar that is to be used must be researched, and then the right model must be selected. The target deployment, the cost constraints, and the features that need to be displayed in the final user interface needs to be determined. All of these aspects have to be factored into the requirements.
And how do we accomplish this exactly?
The product manager works closely with the customer and evaluates the hardware to understand its capabilities to ensure it can support the required features, Arvind. At the end of this process, the product manager creates a detailed product requirements document or PRD.
And what happens once we have our requirements?
With a clear understanding of requirements, the product manager engages a solution systems architect and the project manager. The architect creates a systems architecture document along with mockups, wireframes, and storyboards.
And I presume that at this point, the development can proceed ahead.
Not quite, Arvind. The project manager must first create a project plan and assign resources to the project. Also, these documents must be shared with the customer and approved. At the same time, the project manager must decide on the engineering teams that are to be used for this product and how many resources would be needed from each engineering team. For this use case in particular, the sensor and signal engineering team, the data engineering team, and the applications and algorithm engineering teams were necessary. Each of these teams creates a design document for each of their functional areas. Only then does each engineer begin their implementation based on their design documents.
Thanks, Sohag. Can you describe how the engineering teams partition their responsibilities?
The sensor and signal engineering team acquires and installs the appropriate UWB radar. They simulate conditions that are similar to those encountered in a senior or elder care facility. The radar signals generated from these simulated environments are processed to extract vital signs such as heart rate and respiratory rate. Emergency situations such as precursors to traumatic events are also simulated. All of these signals are passed on to the data engineering team for annotation to create a labeled data set. The data set thus created will have information about the vital signs of the individuals in the senior center along with the emergency events. It may be necessary to augment the data set to create additional emergency events, as it may not be possible to directly obtain this data. This labeled augmented data set is used by the applications and algorithms engineering team to train their model. The applications and algorithms team will create a pipeline to detect and predict emergency events by correlating these with changes in heart rate and respiratory rate markers. I want to mention that each stage in the design and implementation process is overseen by and must be approved by the security, regulatory compliance, and privacy group.
And the next step would be quality assurance, right? As you had mentioned earlier. So what exactly would we need in order to ensure that quality and assurance is done effectively and efficiently?
Arvind, it is important to remember quality must be infused in the process at every stage, from requirements gathering to requirement documentation to architecture to engineering design to implementation. Only then can we ensure that there are minimal defects that get released into the field. At this point, I'd like to make an observation. There is a well-known metric that at each stage a bug is found, the cost to fix it increases by a factor of 5 to 10x. For example, a bug caught in development may take 15 minutes to fix. That same bug, if caught during integration testing, may take a few hours to fix. If that bug escapes to beta, it may take a few days to fix. And if it was found at production, it may take a couple of weeks to rebuild the product and re-release it with the defect corrected. This implies that test cases must be defined at each stage in the process, relevant to the work product of that stage, and quality must be assured at every stage. Nevertheless, after the development comes the formal quality assurance and testing of the software. At this point, we take the functional product modules and requirement documentation to create test cases, execute them, and track bugs. At the end of this process, we have a tested product candidate.
And when does the customer get their hands on the product?
Well, from this point, we move on to stakeholder review. We take the tested product candidate for demonstrations and feedback collection.
Okay. And presumably, all the stakeholders have to complete the review before we can deploy the product, correct?
Correct. Once we have stakeholder approval, we proceed to the deployment and integration. We take the finalized and tested product for deployment to the live environment and integrate it with existing systems. We then have a live product.
Right. It's very important that we ensure all stakeholders are involved at this point onwards, as they are at the very core of the product that we are developing.
Absolutely.
And do we go hands off after deployment, Sohag?
Not quite, Arvind. After launch comes post-launch support and maintenance. We take the live product along with customer feedback and bug reports, and then we undertake ongoing development, patches, and updates.
I see. And how can we ensure that we always improve on this?
For that, we use a feedback loop for continuous improvement. We take user feedback, we take analytics data, we take stakeholder feedback, and then we identify areas of improvement.
Right. And that is all for our product development approach, correct?
Absolutely.
Right. Thank you so much, Sohag. That was a great overview of our product-centric approach as applied to an actual use case in the smart health vertical. Now, let's move on to the next segment of this webinar. I welcome back Dr. Raj Gupta to talk about why Multicoreware is a leader in the context of smart city, smart health, and Industry 4.0 solutions.
Certainly, Arvind. At Multicoreware, we pride ourselves on our technical expertise, innovative solutions, and collaborative approach. Our team is composed of experts in various fields, from machine learning to sensor fusion, who are dedicated to developing cutting edge solutions for SSI. And it is not just about our team and our technology. We also have a track record of success in implementing these solutions in real world settings. We worked on numerous smart city projects around the world, helping cities improve efficiency, sustainability, and quality of life. We have worked with various digital health companies that have developed products and predict the onset of disease based on vital sign detected using a low power radar positioned in a room. And we have worked on projects in next generation industrial application to categorize parts in the factory, detect defects in gear parts and PCB based on super resolution. In short, we have specialized services. Our team comprise experts in various fields, ensuring that we can tackle any challenge that comes our way.
Right, absolutely. And with that expertise comes flexibility and scalability. Can you talk more about this, Raj?
We can adapt to your needs and scale our solutions to match your growth. And while we are doing that, we ensure protection of your core competencies. We focus on our strengths so that you can focus on yours, and this approach also ensures speed to market. We understand the importance of time in today's fast paced world and strive to deliver solutions as quickly as possible. But speed doesn't mean declines. We also focus on risk mitigation to ensure that our solutions are not just fast but also safe and reliable. And once our solution is deployed, we provide ongoing support and maintenance to ensure its continues to serve you well. With our global reach and 24/7 development, we can serve clients from all over the world at any time.
Right. And we always stay updated with the latest technologies and awareness to ensure that our solutions are cutting edge. Collaboration and fresh perspectives are at the heart of what we do here. We believe in working together to come up with innovative solutions. And additionally, we have a group focused on safety, regulatory standards, and compliances to ensure that our solutions adhere to all relevant laws and regulations such as HIPAA, GDPR, SOX, PCI, and many others.
Finally, we believe in training and skill transfer. We don't just provide solutions, we also empower our clients with the knowledge they need to make the most out of those solutions. And that's why you should choose multiple way.
As we come to the end of our discussion, let's summarize the key takeaways from this webinar. We've discussed the journey from sensors to deep learning, delved into technical aspects of smart city, smart health, and Industry 4.0 systems, and explored specific areas where Multicoreware has made significant impact. We've also shared some of our success stories and highlighted how our technical expertise has been applied to overcome those challenges. We encourage all participants to explore Multicoreware's offerings and connect with our team for further discussions. We're here to help you navigate the exciting world of SSI technologies. We'd now like to open the floor for a Q&A session. We're here to engage with you and address any questions you may have related to our framework and Multicoreware's role. Please feel free to ask your questions. We're excited to hear your thoughts and provide further insights into our work. Okay, so we have our first question here. Given the challenges posed by cloud-based video surveillance, like bandwidth limitations and data security concerns, what alternative solutions do you suggest? And what are the use cases where it can be applicable? This one's directed towards Raj.
Yeah. So cloud-based video solutions have a specific case because video has to be transmitted and videos have been megapixels. So the same thing can be looked on the TOF camera-based solutions because they are having same problems, right? Now, what are the different use cases where it can be applicable? The various use cases can be there, but one of the use case can be head detection using the TOF camera, where we have only the point cloud pixels which need to be found out.
Your answer was insightful, Raj. We have another question here. So this question is about quantization techniques. They've heard about post quantization training and quantization aware training programs. They're asking you to elaborate on them and describe the pros and cons. This one is directed towards Sohag.
Yes, thank you for the question. So yes, you're absolutely right. Post-quantization training, PQT, and quantization-aware training, QAT, are two techniques that are used for quantization. The differences between the two are essentially exactly as the name suggests. Post-training quantization is a technique when the neural network is entirely trained using floating point and gets quantized afterwards. So in order to accomplish this, once the training is over, the neural network is frozen, meaning its parameters can no longer be updated, and then parameters get quantized. And what gets into the field is, or what gets deployed in production is the quantized model. And this is used to perform inference. And at this point, there are no changes to the post-training parameters. On the other hand, quantization-aware training trains the neural network using integer weights during the training process. That's during the forward pass, but during the backward pass, the weights that get passed back are essentially floating point. So they get re-quantized at each step during the training. Now, the advantage of quantization-aware training is that there's much lower loss that is involved. So the model is better in some sense, but the problem is that the computational costs of training are much higher. So I hope I answered that question. Please let me know if you have a follow-up.
Thank you so much, Sohag, for your answer. We have one more question, actually. The question follows as, can digital twin technology be applied for anomaly detection in video surveillance? And how does this application differ from the one you showed for Industry 4.0? This one is directed towards Raj.
First of all, anomaly detection is a very concentrated problem in the Industrial 4.0, where we are looking on if any product which has not been up to the standards. But anomaly detection can be applied in video surveillance in limited use cases, like the people are walking and particular person is running. So it is anomaly behavior with respect to other people. But to just take it more, we should not look on that side. Second thing, can the digital twin technology deployed on video surveillance? Yes, we can do it obviously because video surveillance has been a way to represent the data in the avatar world or the virtual world, which is very important for us to understand. Now, how this application differs from the Industrial 4.0, Industrial 4.0 has the physical properties even, whereas video surveillance, it has not a physical properties, but it is all about tracking and simulating the environment only.
That's all the questions we have for today, Raj and Sohag. A heartfelt appreciation for enriching the Q&A session. And we're diligently compiling all the questions, and rest assured, all our registrants will receive these coupled with the webinar recording in the upcoming days. As we conclude today's enlightening session, our profound thanks to each participant for your enthusiastic engagement. It's our sincere hope that you found this discussion both enlightening and enriching. Wishing you a splendid day or evening ahead, and we eagerly anticipate your presence in our future endeavors. Stay safe and best regards to all. Thank you.